This is not teaching. You should read it in the morning. This is garbage.
You guys figure out final project?
Okay, folks, we can get started. So, how's Lab 3 going? So, I mentioned this in the Wednesday and Thursday lectures. The week 1 checkout, the impression seems to be that folks are moving at a very comfortable pace towards getting that checkout done. I think there's just a little bit too much stuff in that checkout. So getting everything done for the first week's checkout seems to have been a little bit ambitious. That's on me, that's not on you guys. To that end, I'm gonna open up some additional lab hours on Monday and Tuesday. I'll post about that on Canvas, and folks are welcome to come and continue to work then. And then I think that the week 2 and week 3 checkouts are more appropriately scoped, I think. But you guys are the guinea pigs, so we're finding all this out as we go along. Any questions from anyone? Any good bugs from anyone? Yeah.
We had one that the accelerometer, the IMU was flipped 180 degrees. And so it looked like the filtered angle would go the wrong way for a second and then correct back to the right way. And then we just put a -1. We multiplied one of the values by -1 in it.
Okay, okay, that works. That's a good one.
Ground was disconnected. So instead of producing a value, it produced a flat line of nothing from the H bridge. Not even the H bridge, but the VJTs before the H bridge.
Okay. So
Ground was connected and it worked.
yeah, folks are discovering that you have to be really cautious in this lab of grounds, because I'll just remind everyone, there's 2 grounds, 2 powers. So your microcontroller and the IMU, the I2C sensor, it has its own power and ground. You power the IMU off the 3.3 volt output of the Raspberry Pi Pico. You attach it to the same ground as the Pico. And then totally separately, the motors have their own power supply that comes from the bench power supply. You're going to power that at 5 volts. And incidentally, we found that powering that instead at 6 volts sometimes works a little bit better. There's about a 1 volt drop through all the circuitry, so you can safely power it at 6 volts. But remember too that then has its own ground. And when you start testing in the coming week and 2 weeks, the motor is going to be running, producing a lot of noise. Just remember that on the oscilloscope, ground is internally connected between the 2 channels. So if you have ground hooked up to, the ground of one of your scope probes hooked up to, say, power supply ground, and then you have the other probe hooked up to something in the motor or IMU circuit, you are coupling the 2 circuits through the shared ground but in the oscilloscope. So just be cautious about that when you're doing your testing. Anything else from folks? Yeah.
Dead IMU.
Dead IMU. So you just, all that you did was replace the IMU and things worked okay?
Yep.
Okay. Okay. Yeah.
Notice that the quick connectors were kind of sus.
Yes. So in the lab write-up, I say something about, you can solder the header pins onto the IMU, or alternatively, come ask me for a quick connector. And these IMUs, the breakout boards, have the quick connect connections from, I think they're an Adafruit thing, that essentially allows for you to not solder those headers if you don't want to. Some groups are discovering that the connection through that connector can get a little bit wonky. So just something to look out for. If you're debugging and something is going wrong with the sensor, maybe don't take that connection for granted. The error might be in that connection. You could test that. Okay. How about final projects? Yeah.
Wait.
Yeah, you go back. Question? You sure? Okay. Final project. So people in the Wednesday lab, I'm going to ask for you to submit your final project proposal on Wednesday. Thursday folks on Thursday, Friday folks on Friday. Does anybody want to talk about that? Does anybody have ideas that they want to kick around with the class?
Next Friday.
Who knows what they're doing? Kind of, sort of. A few groups, kind of, sort of. Okay. So let's talk about it in lab this week. So when I'm walking around lab, just flag me down and we can talk through some ideas as a group. Yeah?
Can you talk about like the proposal itself and like what you...
Yeah, so there's a question about the proposal itself. If you want some details about that, the place to look is on the final project write-up. There's a section here on project proposal that describes the information that I'm hoping to see in the proposal. There's not it shouldn't likely be more than, a page or two. It's not tremendously extensive. What I'm really looking for is just what are you planning to do and an approximate plan for how you're going to put this thing together, what the associated hardware is going to be, just some evidence that you've thought it through a little bit. And largely what I'm doing is, like I've said before, I'm just kind of sanity checking it. I want to make sure that the project you're proposing isn't scoped for something like, a full master's project or a full PhD project, and likewise that it's not inappropriately easy. And I also just want to make sure that it's not going to damage anything in the lab or damage yourselves or anyone else in the lab or me. So I'm just looking out for these sorts of things. But yeah, this is where information about that lives. And I'll put a assignment on Canvas. I'll do that either today or tomorrow morning so that you can just submit the proposal through Canvas. Okay. Anything else? Yeah.
Assume I'm creatively bankrupt. What do I do?
Oh, I'm glad you asked. How do I come up with an idea? This generally encourages you to do what I've talked about before, which is it's a process that you might consider going through for coming up with an idea. Largely, it involves writing down the stuff that you're curious about, your hobbies, and then talk with your group mates, talk with me, with Bruce, your TAs, and we can come up with a project that allows you to explore one of those things. Or alternatively, and additionally, browse through projects from previous semesters. So these are all the projects from this course all the way back to 1999. Back when this course was taught in assembly. Yeah. So all of these projects were written in assembly. So going through this list is first of all just interesting. I mean, the range of projects here are unbelievable, but also it can be a good source of inspiration for your own project. So look through this list as well. Okay, I'm going to bring in, just speaking of this class throughout history, I have the hardware that this class was taught with in 1984. At that time, if you were a student in this class, you got what looks kind of like a wooden briefcase that includes a full breadboard, power supply, all this stuff. And what the students were doing at that time is implementing TTL logic on this thing. Microcontrollers weren't really around yet. It's called this, I can't remember. It has a slightly different name. I can't remember the name of it. But I'll bring in the device and show you what it looks like. It all still works, by the way. You can power this box up and it still all just works just fine. I'll bring it in and show you next time. Okay, any other questions? Questions about final projects, questions about lab 3, questions about problematic bugs? Yeah.
If we want to do the 1 credit add-on later on where we write it up, is there anything we should kind of keep in mind while going through this final project stuff?
Not really. So the question is about, on the course webpage, if you scroll down to the bottom, there's a Life After ECE 4760 section, and there's a course that I'll teach next semester called 4920, where we take your final project and we'll turn it into a magazine article and try to get it published. You don't really need to worry about this at all at this point. All of the exercise associated with translating your final report into something more appropriate for a professional publication we'll do as a part of that class. You don't need to worry about it at this point. By the way, you might also be interested to go through the, let me see here. These are the projects we published last year, which you could also read through if you wanted to, mostly in Circuit Cellar magazine, one in Servo. Okay, anything else? Any issues in the assembly instructions for the inverted pendulum? Relatively okay. Yeah. Okay, then let's carry on. So what I'd like to do today then is continue going over the content that's of relevance for this week's checkout in Lab 1. We started a conversation about the I2C protocol last week. I'd like to quickly review the stuff that we talked about, not last week, last lecture. I'd like to quickly review the stuff that we talked about in the previous lecture, and then carry on to finish the discussion about the I2C protocol in general, and then we'll talk about the I2C peripheral on the RP2040 in particular. We'll look at the example code that you all are working with for the IMU. So let me just remind you that hooking up an I2C bus is, as compared to some other communication protocols, rather simple, because there's only one clock line and one data line, and that clock and data line is shared between every controlling device and every peripheral device. So you can see that SCL here is connected to everybody, and SDA is connected to everybody. Each of these lines is pulled gently up by pull-up resistors. So when no transactions are occurring, the lines are high, logic level high. And as I mentioned last time, this wiring diagram suggests one of the important differences between I2C and something like SPI, which is because there's only one data line, this correctly suggests that data is only ever flowing in one direction, right? As SPI, we had two data lines. We had MOSI and MISO. The MOSI was data flowing from the master device into the slave devices, master out, slave in. And at the same time that data was going this way on that data line, data was coming the other way on the other data line. So we had full duplex communication. That does not exist in I2C. So you could say that one of the benefits of I2C perhaps requires less I/O ports. One of the costs perhaps is you're not going to be able to get speeds as fast as something like SPI, because you can't do full duplex communication here. So how does a transaction actually work? Suppose that I'm a controlling device and I want to communicate to some peripheral device. How do I make that happen? Well, because the clock and data lines are shared among everybody, perhaps it stands to reason that the first thing that I have to communicate to everybody on the bus, well, the first thing I have to do is take control of the bus. So if I'm a device that wants to control the bus to take a measurement from some peripheral device, I first have to indicate to everybody that I'm in charge. And I indicate that, as I mentioned last time, through a start condition. A start condition looks like this, where the device that wants to instantiate a transaction, it will transition the data line from high to low while holding the clock line high, and then it will transition the clock line from high to low. This is understood by every I2C device on the bus as a start condition, and once the other controlling devices that may be on that bus see this, they relinquish control of the bus to whoever generated this start condition. So in your case, the device generating this start condition will be the RP2040, and the device that notices it will be the IMU. Not that the IMU acts like a bus master anyway, so there's nobody competing in this particular case for control of the bus, but suppose you had two RP2040s on the same I2C bus, this would be the indication from one to the other that I'm in charge for right now. And then because everybody is sharing data lines and everybody's sharing a clock line, it should probably stand to reason that the first thing that has to be communicated is, who am I trying to talk to? So there may be some number of sensors or peripheral devices on this bus. The first thing that I have to communicate to all of those devices is who should listen to this transaction and respond. And the way that I indicate that is by putting a 1, 2, 3, 4, 5, 6, 7-bit address out onto the data line. So after this start condition, there are going to be 9 clock pulses, 1, 2, 3, 4, 5, 6, 7, 8, 9. The first 7 of those clock pulses will include the address of the device with which we're trying to communicate, most significant bit first. The 8th clock pulse is a read-write bit. Do I want to write information to that device, or do I want to read information from that device? That's indicated by this read-write bit. If that is a 1, then the controlling device, the RP2040, is requesting data, perhaps from the IMU. If it's a 0, then the controlling device, the RP2040, is writing data. Perhaps we're configuring the gyroscope sample speed or something like that. We're going to write to one of the configuration and control registers. We indicate that we're going to do that right through the read-write bit. And then on the last clock pulse here, there's an ACK. So for this last clock pulse, the controlling device, the RP2040, relinquishes control of the data line And if this address and read-write information has been understood by the device with which we're trying to communicate, the device with this address, then it will hold the data line low for that last clock pulse. And that's the indication to the RP2040 that message was received and we're ready to proceed. If alternatively this was high, suggesting that the pull-up resistors just pulled it high, the message was not received, that fails the transaction and probably we try again. Or we fix some error we made, like maybe we put a typo in the address, right? So we're trying to communicate with a device that doesn't exist, or something like that. And then the next thing that will happen will be a 8-bit transaction, so data bits on each of the clock pulses, followed once again by an ACK, and then the whole transaction concludes with a stop condition, which is sort of the mirror image of the start condition. The stop condition is the clock line transitioning from low to high while the data line is held low, and then the data line transitioning from low to high. That indicates to every other controlling device on the bus that this transaction is complete, and some other device that wants to communicate with a sensor could make its own start condition and relinquish control of, and take control of the bus to do its own transactions. So you can see 9 clock pulses per transaction, 8 of which are data of some variety, and the final of which is an acknowledgement from the device that we're communicating with. Questions about that? Yeah.
So because the stop condition is like required to like say to like kind of relinquish control, if like let's say a core was sending something and it crashed or something along those lines, would it just be like, all right, forever I2C is belonging to that core or whatever, and you can't touch it anymore?
That could be the case. It could be the case. You can set up, it is often the case, particularly with microcontrollers, that you can set up these I2C transactions with timeouts. So you could say, do this, and if this much time passes and nothing has happened or we haven't relinquished control of the bus, then time out the transaction. But yeah, it is something that you'd have to be cautious about. So you can see the timing diagram's a little bit, what's the word? Less obvious or something than SPI. On SPI, you pull it up on the scope and it's pretty clear what's going on. It's a little bit more subtle, right, with these start conditions that you'd have to look out for on the scope and the stop conditions you'd have to look out for on the scope. So debugging it on the scope is perhaps a little bit trickier. That said, there's only one clock and one data line, so with a 2-channel scope, you get the whole communication story. So that's kind of nice. Okay. And like I mentioned last time, we're going to look at the data sheet for the IMU in just a second as sort of a case study of this, but 7 bits of address here suggests 2 to the 7th minus 1 possible devices on this bus, and in principle, okay. In practice, it's often the case that you have either no freedom in setting the address of the device with which you want to communicate, or really limited freedom. So for instance, I've worked in the past with an I2C temperature and humidity sensor. That device's address is hex 40. So you can't change that, which means you only get to put one of those devices on the bus because you can't have 2 devices with the same address on the bus, right? The MPU 6050, the IMU that we're using in Lab 3, we'll look at this in just a moment, but you have the ability to choose between one of 2 addresses for this particular device, which means you could put 2 of these devices on an I2C bus. There are tricks that you can pull for getting more devices with the same address onto the bus. You set up what essentially looks like a chip select line, an additional GPIO port that communicates with each device that says I'm talking to you or you or you. You can do that. Students in the past have done that with success. You start to sacrifice some of the advantage of I2C when you're doing that, because then you're just adding more GPIO ports, and one of the advantages of this is the limited number of GPIOs.
What are like the challenges associated with having more freedom to choose your addresses?
What are the challenges associated with that?
You have no freedom or limited freedom. Why is that?
Why is that? I don't have a good answer to that question. I expect that the answer probably has something to do with the manufacturers of the device. It makes the devices slightly simpler, which perhaps makes them cheaper or something. That would be my best guess. But yeah, it is rare that you have total freedom to select an address. There's a project that I'd love to see actually in this class, which is, if you look at like the gyroscopes that are used for spacecraft, a common one is the LN200 from, I think it's from Northrop. Look at the price tag of it, and you could either buy that gyroscope or like a pretty nice house, right? That's about how much they cost. I think it'd be really neat to try to build a device that arrays a few hundred very, very low cost gyroscopes, samples all of them very quickly, tremendously overdetermined system, and then run an estimation algorithm on all the gathered data to see if you can get an estimate for a rate that is competitive with a super, super high fidelity gyroscope by trading computation, which is cheap, for sensor fidelity, which is expensive. I think that would be cool. There's one guy who was working on this for a little bit, John Christian, and did it with some success, if I recall. But anyway, I think that would be an interesting thing to try, just with a handful of sensors. See if you could run an estimation algorithm on a handful of sensors and get an estimate that is as much better than the measurement from any individual sensor as you would expect, given the number of sensors that you have and the statistics of their noise profiles. Okay, a couple of other things just quickly mention about I2C. Something else to be aware of is this notion of clock stretching. So I mentioned that that last clock pulse is an ACK from the device that we're communicating with. Suppose that we're communicating with some device and we say, we would like for you to go get a measurement. And suppose that device needs a little bit of extra time to go and do whatever we've asked of it. One of the things that these devices can often do is clock stretch, which is the peripheral device, the device with which we're communicating, will hold the clock line low for a little bit of extra time. So we'll add some delay before that last clock pulse. And then it releases control of the clock line to allow for that pulse to occur and gives its ACK. So it can buy itself a little bit of extra time to do whatever we asked of it. So, and it does so by adding a little bit of extra time between the 8th clock pulse and the 9th clock pulse, called clock stretching. So you may see this on the oscilloscope. With the IMU, I believe, does this. So if you pull up the I2C transactions on the scope, you may see some extra time between the 8th and 9th clock pulses, and it's because the IMU is clock stretching, buying itself a little bit of extra time to do whatever we ask for it to do. Another thing that you can do is, suppose I'm the RP2040 and I want to, oh, I don't know, read from the gyroscope and the accelerometer, and I do not want to relinquish control of the bus between those two transactions because they're time sensitive. I want them to be taken one right after the other. These transactions, generally speaking, are 8 bits, but the controlling device, can do a trick, which is this repeated start condition. So you can see that this here is the end of the first transaction. This is the 9th clock pulse. The device has sent an ACK, right? So this has been a successful transaction. What the controlling device, can then do is transition the data line from low to high while holding the clock line low, and then transition the clock line to high. This, you will recall, if we look back at that timing diagram from previously, this is not a stop condition. A stop condition is transitioning the clock line from low to high while holding data low, and then transitioning data line high, right? So at the end of a stop condition, the state that we end up with, or the state that we end up in, is both clock and data lines are high. That's the state associated with nothing happening on the bus, right? So after a stop condition, we're back to just both lines high. In a repeated start condition, we do this data line transition from low to high, followed by a clock transition from low to high. Like I just said, that's not a stop condition. It does not relinquish control of the bus from the device that did this transaction to some other device that might take control, but it puts the clock and data lines both high again. So it puts the bus back into a state where the first controlling device, the one that wants to retain control of the bus, can do a new start condition and then do another transaction. And between the end of this first transaction and the start of this second transaction, there was never a stop condition that relinquished control of that controlling device to some other device. Right? So if I have a handful of transactions that are time sensitive and I don't want for anybody else to interrupt me while I do it, I can put repeat start conditions between each of those transactions, and then no other device will interrupt me while I'm communicating. Okay. And the last just brief thing that I'll mention is 10-bit addressing. You can set up this bus for 10-bit addresses, which is what it sounds like, instead of having 1, 2, 3, 4, 5, 6, 7, 8-bit addresses. Or I'm sorry, it would be 7-bit addresses, and this was a read-write indication. So instead of 7-bit addresses, we have 10. This, as you might expect, gets divided up into essentially 2 transactions, so that first transaction where we're indicating the address of the device we want to communicate with, that happens over 2 transactions. The first one, the most significant 1, 2, 3, 4, 5 bits will be 11110. And we're making the assumption that there are no devices on this bus with an address that starts with 11110. And then we'll have the most significant bit of the address for the address of the device we're trying to communicate with, the second most significant bit, and a read-write indicator. And then this ACK will come from every device on the bus with these 2 bits as the most significant bits of their address. So all such devices will ACK together. They all collectively hold the data line low. Then we do a follow-up transaction that includes the rest of the address. And at this point, there is now only one device on the bus that has that full 10-bit address, and only that device will ACK. And now we've indicated which device with a 10-bit address we want to communicate with. So in brief, that's the protocol. None of that is RP2040 specific. That's just I2C. By the way, when you see I2C in documentation, you might also see I2S, you might also see TWI. They all kind of mean the same thing. I2C, as it turns out, is a trademarked name of Philips, I think, the company. So in some documentation, you will see different vocabulary used to describe essentially the same protocol, and it's to avoid any legal implications associated with maybe using I2C. Yeah?
Some call it two-wire.
Yeah, TWI, two-wire
Something like that.
interface or something like that. Yes, you'll see that as well. Just something to look out for. Okay. So let's look at the data sheet for the MPU 6050 in particular. MPU 6050 data sheet. And I just want to point out a couple of things about this. So there's a bunch of stuff here. Let's take a look at, I2C interface looks promising. So the first thing I want to point out under the I2C interface is this sentence here. The slave address of the MPU 6050 is this. And your degree of freedom in this address is the least significant bit. And you choose among you choose one of 2 possible values for that least significant bit by setting the logic level on one of the input pins. So there's an input pin to the MPU 6050. You set it high, you get one address. You set it low, you get the other address. Okay, which is just to point out that you don't have total freedom over that address in this device, and that's what that is telling you. And then if we scroll a little bit further, what we'll find is a description of how these transactions occur. And this is essentially it's showing you in a data sheet the same thing that I just showed you on a slide. I just want to show you that this lives in data sheets for devices like this so that you can go look at it and understand what it's telling you. So what this is showing is, say we want to do a single byte write sequence that starts with a start condition. The master device sends out a start condition that gathers control of the bus, followed by an address plus a write indication. right? Address followed by that read-write bit is set to write, followed by an ACK from the device we're communicating with, the register address from which we want to read, followed by an ACK, the data, followed by an ACK, and then a stop condition, which describes exactly the timing diagram that we just looked at. And here's your little table of what all these symbols mean. Okay. So we talked about the I2C protocol in general. We looked at, a little bit of the data sheet for the particular device that we're talking about. I'd like to now look at the demo code for this week. A couple lectures ago, we looked at the PWM demo, so we've talked through this quite a bit. I'd like to look at the IMU demo. And in particular, let's look at so this IMU demo.c file it's the source file that contains main. And we'll talk through this in a second, but that's what that is. What I would like to start by looking at are the two header files associated with the MPU 6050. They implement just a very, very simple API to this device. And I want to talk through what those functions are and how they work and connect it back to the conversation we just had about I2C. So the header file here, all that this is doing, as you'd likely expect, is setting the address of the device that we're communicating with. So that is the I2C address of the MPU 6050 as gathered from the data sheet. Right, so we went to that section of the data sheet, looked it up, that's what it was. This is the I2C channel that we're going to configure. Remember that the RP2040 has two I2C channels. It also has two SPI channels. It also has two UART channels. We're just indicating that we're going to use I2C channel 0. These are the two GPIO pins that we're going to map to the two I2C lines. And we're specifying the baud rate, which we could have found. We find this in the data sheet as well. The data sheet will specify the baud rate for the device we're communicating with. Okay, and then we've consolidated our fixed point macros for this particular example into this header file as opposed to our main source code. Okay, and some other macros here for doing some fixed point arithmetic. Just all I'm doing here is defining some constants in fixed point. So this is 180 over pi. Looks like this in fixed point, and that's so that we can do unit transactions or conversions quickly in fixed point. 0.001 is this, 0.999 is this, and so on. These are for you to play with in your complementary filter, right? Just some handy predefined values that you could plug in and play with for your complementary filter. And then down here, there are a couple of functions that we'll just go take a look at in a moment. One is MPU 6050 reset, and the other is MPU 6050 read raw. So then if we go into the .c file, which implements these functions, let's take a look at, I want to just take a look at like one or two of these lines because it's all pretty, it's kind of repetitive once you see what's going on. But for instance, let's look at, in the MPU 6050 reset, what this function is doing is resetting the device and then doing some configuration of the device. What is the sample rate that we want to use for the gyroscope? What's the sample rate we want to use for the accelerometer? What's the resolution we're selecting for each of those? There's some degrees of freedom there that we can select. So let's just take a look, for instance, at lines 18 and 19. You can see that we've declared an array of 8-bit characters called gyro rate. The value at the first index of this is hex 19. As we'll see in just a moment, that is specifying a register address in the MPU 6050 to which we are going to write a configuration. And then the second 8-bit sequence here is the data that we are going to write to address hex 19 in the 6050. We then call a CSDK function for the RP2040, I2C write blocking, which does exactly what it sounds like. It does a write over the I2C channel. It's over I2C channel 0. It's to the address that we just looked at the top of the header file. So this is saying we're writing to the IMU. We are writing 2 characters, and we're pointing it to the start of the array that we would like to write. and false we'll look up. Can't remember what that argument is. Okay, so what this is saying is write 2 bytes over the I2C channel to this address. And in particular, write first this byte and then write this byte. I want to just briefly step back into the MPU 6050 datasheet so that we can connect these somewhat cryptic numbers to their place in the datasheet so that you can go look at this stuff yourself. MPU 6050 register map. This is an example of a sensor that consolidates all of its registers into a different document. Okay, a little annoying, but that's fine. So let's look at register hex 19. Let's see what that looks like. So 19. 19 is hex 19 sample rate divisor. And then let's just scroll down and look at what that is doing. You can scroll down here to hex 19. And what this is indicating is what each bit of that 8-bit sequence represents. So you'll remember that we were writing 0, 0, 0, 0, 0, 1, 1, 1. And if you read below this register description, it describes precisely what each of these bits does. And in particular, what the value in this register is doing is setting the gyroscope sample rate to the gyroscope output rate, which we see here in the data sheet is 8 kilohertz, divided by 1 plus whatever value we put in that register. We put in 7 into the register, 1, 1, 1, that's 7. 7 plus 1 is 8. 8 kilohertz divided by 8 is 1 kilohertz. So we're setting the sample rate of the gyroscope to 1 kilohertz. If you wanted to, you could go through a very, very similar exercise to investigate what exactly are the settings that are being configured here in this line. In this case, we're doing a write to address hex 1B, and we're doing all zeros. Or in this case, we're writing to address hex 1C, and we're writing all zeros. You could go through the process that we just went through, where you go into the register map, you look up this address in that register map to see what it's doing. You scroll down and read its description, and then you could see what each bit in that register does. What we're doing here is popping down a level of abstraction below where you will likely be working, right? But like I've said a number of times, whenever a level of abstraction is hidden from you, I want for you to know what's hidden. So if you want to, that's how you can go investigate what's going on here. And by the way, there's a lot of configurations that are possible for this sensor. So you could go in, if you cared to, I don't necessarily recommend it, and change these. You could change the sample rate of the gyroscope. You could change the sample rate of the accelerometer. You could change their ranges. So right now the accelerometer is set up to sense acceleration in the range of +2 to -2 Gs. The gyroscope is set up to measure a range of rates in a range that I can't recall, but it's some number of degrees per second that it's sensing. You could change those ranges if you wanted to. Or you could do a lot more different configurations, right? And that's how you would investigate what those configurations are. And then the only other thing that I'll just briefly point out is this read raw. What this is doing is slightly different. All of the configurations were I2C writes, right? We were writing to registers on the MPU 6050 to configure it. In this case, what we're doing is reading data from the IMU. In particular, we're reading from the addresses where the gyroscope data gets stored and the acceleration data gets stored in each of the 3 dimensions, right? X acceleration, Y acceleration, Z acceleration. And likewise for gyroscope. So in particular, we have some buffer of characters and a couple of 16-bit temporary variables. We start reading from address hex 3B on the IMU, which we could look up, and what we would find is that's the start of the registers that hold the measurement information, and then those are all arranged one right after the other so that we can do subsequent reads from that start address and got all the information that we want. for the accelerometer. We do a write blocking to the address specified here, indicating that we would like to start doing a read. And then we read 6 characters. 2 characters for x acceleration, 2 characters for y acceleration, 2 characters for z acceleration. And those all get stored in this temporary acceleration measurement variable. Okay, so it's a function that as an argument, it takes 2 arrays of length 3 and of type fix15. And what this function does is set the values of those arrays to the most updated measurements as read from the IMU in fixed point. So there's some unit conversion that occurs here where the data that gets stored in the acceleration array is in units of g's, represented in a fixed point data type. And likewise, the data for the gyroscope measurements is in units of degrees per second in fixed point, and it gets stored in the array that you pass in. Questions about this? Again, this is largely FYI. Okay. So then, let's look at the actual demo code which you will be modifying. And let's start by scrolling down to main and just taking a look at what's going on. So we do a bunch of familiar looking stuff, stdio init all, we initialize the VGA screen. We then set up our I2C channel. So we call I2C init. We pass as an argument which of the 2 I2C channels are we initializing, I2C channel 0 or I2C channel 1. We've pound defined I2C chan to I2C 0. So we're initializing I2C channel 0 to the baud rate, which we've also pound defined in the header file for the IMU. We then associate 2 GPIO pins with their I2C functionality. These 2, you'll remember, were pound defined in the header file or the source file, I can't recall, for the IMU, right? So in particular, one of these is GPIO 8, the other one is GPIO 9. We're mapping those to their I2C functions. And so that we don't have to breadboard external pull-ups for these pull-up resistors, instead of breadboarding external pull-ups, we are using internal pull-up resistors. So we're enabling pull-ups on each of those GPIOs. It's kind of handy. We then call MPU 6050 reset, which is the first of those 2 functions that we just looked at. And like we saw, all that this is doing is resetting the 6050 and doing some configuration of things like sample rate and measurement range. And then we call read raw to gather a first set of measurements that will get populated into the acceleration and gyro arrays. Each of these are fixed point arrays of length 3. We just do 1 measurement. We'll see how that's used in just a moment. For your convenience, this example also initializes PWM outputs on GPIOs 4 and 5. Some of you were playing with this in lab this week. You'll remember that GPIOs 4 and 5 are both on the same PWM slice. They're both on slice 2 of the PWM peripheral. So this is setting that up for you. In particular, it's mapping GPIO 4 and GPIO 5 to their PWM functionality. It's looking up the PWM slice that these 2 are on. We're doing it just for GPIO 5, but by looking at the data sheet, we know that it's the same for GPIO 4. We are setting up the interrupt for that PWM slice, right? So we're clearing the interrupt if it happened to have been set. We're enabling the interrupt for that particular PWM slice. We're associating a function with that interrupt. We'll look at that function in a moment, but essentially all it's doing in this example is clearing the interrupt and I think setting a semaphore or something like that. And then we're turning on this PWM interrupt wrap interrupt. We're setting the wrap value and the clock divider for that PWM channel. Remember that it's these 2 things that set the period of the PWM channel. And then we're setting the duty cycle of each of those PWM outputs to some arbitrary initial starting value. In this case, it's just a 0, which is to say they're both just grounded. And then we turn on that particular slice. The next thing that happens here in main is we reset and launch core 1. We can take a look at what core 1 is doing in just a second. And then we also add a proto thread to core 0. This is the thread that we're adding to core 0. You can see that it's doing very familiar looking things. So in particular, it's asking the user to input some number. And user inputs some number. And in this particular example, if the user has input an int greater than 0, the value of that int that the user has input gets stored in this threshold variable. And we'll see how that's used in just a second, right? But all that we're doing is asking the user for a number, and then that number gets put into a variable, something that you all are familiar with from Lab 2. And then this is the thread that's being added to core 1. What this thread is doing is all of the VGA manipulations. So those of you that have run this example, what you know that this example does is it generates 2 real-time plots on the VGA screen. The top plot is just all the raw measurements out of the gyroscope. The bottom plot is just all of the raw measurements out of the accelerometer. It's this thread that's doing all that VGA stuff. And we can talk through this to the extent that you all want to. What you will be asked to do in this lab is use this as a template and as a starting point, and you'll replace the content that's in that top plot and in that bottom plot. You'll replace the raw measurements with instead a plot of the complementary filter output, appropriately scaled to the vertical range of the plot, so that as you as you move your pendulum back and forth, we should see your complementary filter output move back and forth between plus a handful of degrees, minus a handful of degrees, and so on. And one of the things that we'll look at is that complementary filter in a bit more detail to help substantiate that. But the other thing that's interesting to plot on the same graph, if you care to, is the measurement as estimated directly from the accelerometer. That's one of the inputs into the complementary filter, but you could plot that alongside with the complementary filter output. And likewise, you could plot the gyro estimate along with the complementary filter output. And what you would observe is a noisy estimate out of the accelerometer, a drifting estimate out of the gyroscope, and the complementary filter output, which is not too noisy and not too biased, right? Giving you the best of both worlds. It'd be kind of interesting to plot all 3, I think. That'll be one of the plots on your real-time display. The other one will show you the motor control input. It'll be a similar graph, but what it will show you is the duty cycle that you have set for the PWM channels that are controlling the motor. And you might consider using a convention where positive values on the graph mean the motor's turning one direction, which is to say it's the PWM signal. One of the PWM channels is 0, the other one has some duty cycle. Positive values represent the duty cycle for that channel, and then negative values would represent spinning the opposite direction, right? So the other PWM channel is being duty cycled, and the first one is 0'd. So it's those 2 pieces of information that you're asked to display. And you'll have to do things, once you get the PID controller implemented, you'll have to do things like low pass that PWM input, because it's going to be quite noisy from interrupt to interrupt to interrupt. That display, though, is really critical for debugging this lab, because what it will then allow for you to do is observe as the motor moves, right, and you see your complementary filter output achieve some angle. You'll see the control input that your PID controller is generating in response to that angle in real time. Super helpful for debugging, right? So that's why I'm asking for you to implement this stuff in early on in this lab, so that you can use it in subsequent weeks. Okay. Questions?
Will the complementary filter work in space? Because there's no G.
That's a good question, yeah. The question was, will the complementary filter work in space because there's no G's, so you don't really have acceleration? A complementary filter would work, but you would need a different set of sensors. So a common set of sensors might be a sun sensor. Where's the sun? and a magnetometer. What's the local direction of the magnetic field? You'd solve the attitude problem with those two vectors. Often it's the case that if you launch like a CubeSat, it usually has a sun sensor, it often has a magnetometer, and then it almost always has a gyroscope. And those are often the sensors that go into solving the attitude control problem in space. Yeah, the accelerometer doesn't get you very much. Maybe some rotation information. Any other questions? Okay, sounds good. Then I will see some of you very shortly.